All right, welcome everyone. My name is Vince Sprinkle. I'm the senior advisor here at PNNL and host of our Energy Storage at PNNL webinar series. In this series, we've been exploring some of the R&D that we're doing at the lab and how that impacts the overall efforts to deploy more grid-scale energy storage. And then also look at how this is tying into the new Office of Electricity capability that's being set up at PNNL and the grid storage launchpad that is set to open at the end of 2023 here, which is aimed at taking those new technologies all the way through the development process and validating those. Today, our focus is on cost and performance of these energy storage systems. We all know that, understanding, what the cost of those systems are, how they perform, what's the expected lifetime is a critical metric as we're looking at the deployments. And we're happy to have Kendall Mongird and Vish Viswanathan to talk about the work that's being done in the updated 2022 Energy Storage Cost and Performance Assessment. And so this work was done as part of the DOE Energy Storage Grand Challenge. And so we'll turn it over to them. Let me do a quick introduction of my speakers. But first, I want to note, as we go through it, please put any questions you may have into the chat window. We will allow them to go through their presentation, and then we will answer Q&A at the end of the session. So please keep those questions coming, and we'll get to them here. So with introductions, Kendall Mongird is a research economist in the Economics, Policy, and Institutional Support Group at PNNL. Her work is focused primarily on integrated multi-sector, multi-scale modeling, energy storage cost and performance analysis, and distributed energy resource valuation. Vish Viswanathan has over 15 years experience in energy storage and fuel cell R&D. Energy storage work includes data health determination, battery sizing, electrode design to optimize power and energy, safety analysis, and design and development of different chemistries such as lithium ion, sodium sulfur, and redox flow batteries for stationary grid storage applications. He is responsible for battery selection, cost estimation, and sizing of energy storage systems for transportation and stationary applications. So please join me in welcoming our speakers today. And with that, Kendall, I'll turn it over to you.
All right, thanks, Vince. Let me see if I can get my screen up and loaded. Okay, hopefully everybody can see that and I can get going on that. All right, perfect. Thank you. Okay, so thank you, Vince, for that introduction. I'm going to kick things off by just giving a pretty high-level overview of the 2022 Energy Storage Cost and Performance Assessment in our database, sort of set the stage, tell you what this project's about. I'm just going to take a couple slides, and then I'll hand it off to Vish to go into a bit more detail on our methodology and go into talk about how we develop these cost and performance assessment estimates for each of the technologies. And then I'll take it back again at the end to walk through some of our comparative analysis of our installed costs estimates and the LCOS, levelized cost of storage estimates as well. So just to kind of set the stage here, the 2022 Energy Storage Cost and Performance Assessment is a report that's built off of the 2020 Grid Energy Storage Technical Cost and Performance Assessment. As Vince mentioned, it's part of the Energy Storage Grand Challenge, and the overall idea is to create this publicly available database where DOE and industry can access pretty detailed cost and performance estimates for a range of energy storage technologies, both for today and projections out to 2030. The 2022 report adds on to the 2020 report by including some new technologies. We also update the estimates that we provided in 2020. And then we're also including estimates for a wider range of power capacity and storage duration combinations. So as mentioned, we've got a pretty good list of technologies that we evaluate there. You can see them on the top left corner there next to that diagram. We have lithium ion, LFP, NMC, lead acid, vanadium redox flow, zinc, pump storage hydro, compressed air, hydrogen, thermal, and gravitational. So we have a lot of technologies, and then we also evaluate them at the power capacity and energy duration combinations that you see in that diagram there with those blue filled in cells. So we collect a lot of information. Not only are we doing estimates for 10 different technologies at those various power and energy combinations, we're also providing low, point, and high estimates for each of those. And then, as mentioned before, we do 2021 and 2030 estimates. So in total, we have over 1,000 total installed cost estimates. And then we also go into detail. We're not just giving these total installed costs, we're also going into the various components of these systems and providing cost estimates or performance estimates for each. So in total, this report has over 14,000 individual cost and performance estimates. So there's a lot of detail, a lot of information. And this diagram on the right-hand side here is demonstrating another part of this effort, another part of this project, which was to sort of build a framework that would allow us to harmonize how these various cost and component terminologies are used. So there's a lot of mismatch out there in how these various components for storage systems are talked about. So part of this effort was to provide this framework, provide kind of an easy building block to be able to talk about these various systems. So lots and lots of information, and I'm going to hand it off to Vish here so that he can start going into a little bit more detail on how we developed all these cost and performance estimates. And then Vish, whenever you're ready. Vish, you're muted. There you go. Oh. There you go.
Yeah, I was having a race with Lara. I think I was unmuting and she was muting. So yeah, I would like to thank Courtney Stenson for staying up late yesterday, 11:50 up to 11:50 p.m.
You may need to move your microphone up a little bit
to format the slides. And I also would like to thank Vince Sprinkle, the brains behind this project. I hope you can hear me loud and clear now, everybody. So this is the heart and soul of our project is this chart here. I won't spend a lot of time on it. You can see the batteries are on the left, then hydrogen followed by pumped storage, gravitational, compressed air, and thermal. In the previous slide, Kendall had the storage block balance of system, and then power equipment. I'm reading the leftmost column here, controls and communication system integration. And for batteries, most of them follow the same pattern. For pumped storage, the reservoir, the storage is essentially the reservoir where the water is stored, and the power equipment is the electromechanical powertrain such as pumps, turbines, and motors. Whereas for batteries, it is the power conversion system and DC converter for power equipment, and the lithium-ion, the battery modules, and the electrolyte tank. Those would be the storage for battery systems. And for compressed air, it follows the same pattern as pump storage. Whereas gravity and thermal kind of follow each other. You got your electromechanical components for both. And the very bottom, you got engineering, procurement, and construction fee, project development, and grid integration for gravitational and thermal. Whereas for pump storage, what you have is a contingency fee of 33% of all the costs above, direct costs. That takes care of the EPC, project development, and grid integration. Next slide, please. Thank you. So the general methodology, Vince brought this up, what is price, what is cost? So he came up with this notion that hardware would be price, cost would be cost for operation and maintenance. We derived price from multiple sources, as Kendall had highlighted in her slide, about 75 sources. And we had scaled price information from vendors for various power and energies levels. All that means is if somebody gives us price for 10 megawatts, if you want price for 100 megawatts, we apply some kind of a discount. Learning rates for well-established technologies like lithium-ion, we deploy the standard learning rates, a formula where if the learning rate is 10%, then for every doubling in deployment, the price drops by 10%. But Vince advised me back in 2017 that for non-commercial technology, the learning rate is not a very good approach. And this was seconded by Lawrence Berkeley Laboratory when we had a call with them about a year ago. So Vince, I would say, was ahead of the curve there. Hence, we used a fixed price drop based on developer input. And then cycle life versus calendar life, what dominates? I will give you a very simple example. If the cycle life is 2000 cycles and you are doing 400 cycles per year, then you get 5 years of life. Whereas if the cycle life is 10,000 1,000 cycles and you're doing 400 cycles, you get whatever that is, or way more life, right? In that case, in the latter case, the cycle life doesn't dominate, whereas in the former case, due to the cycle life, you have to replace the battery. There could be some question as to why we don't use greater than C/2 rate for that is because for grid scale storage nowadays, the duration is going greater or equal to 2 hours. We set plant life as 20 to 25 years for battery energy storage systems and greater than 30 years for the rest. Next slide, please. Okay, so what is the general methodology for battery energy storage system? On the right, you can see the various components, storage blocks, balance of system, power equipment, controls, and communication. Below that, you got system integration. Below that, EPC, project development, grid integration. The DC storage block price obtained from various vendors, and we apply a certain reduction, as I mentioned earlier, for every order of magnitude in energy. Balance of system would be the container, for example, and the various connections and for lithium-ion batteries. It would mean something else, such as pumps, pipes for flow batteries. So we assign that as a percentage of storage block cost, and then apply the same scaling in terms of energy based on whether the energy increases from 1 to 3 or 10 megawatts, or whether it increases from 10 megawatts to 100 megawatts. We use a bidirectional inverter, or a fancy term for that is power conversion system. And we assign a certain percentage decrease for every 1 order of magnitude increase in power. For certain technologies like lead acid battery and flow batteries, we need a DC-DC converter to maintain a stable voltage. And we have a certain percentage decrease for every 1 order of magnitude increase in power. Next slide, please. So this has been used for lead acid and flow batteries. Thank you. Controls and communications, we found that in the literature, the costs are reported excessive. So we came up with a methodology. Richard Baxter, who is not here, had a lot to do with this methodology, along with Charlie Vertanian for power equipment. Non-recurring energy engineering costs, we assigned a certain NRE for a project. And then for data pipeline hardware costs, we assigned some costs. And then we assume that this hardware cost increases by 2 times for every order of magnitude increase in power. And then total cost integration cost decreases by 50% for every 10x in power. This decrease in 50% is per kW. Then we assign certain markups for system integration, engineering, sorry, my typo here, engineering, procurement, and construction, project development. And the way you do that is for system integration, you assign markup to all the elements above. For engineering procurement, you assign the markup to all the elements above, and project development, you assign the markup to all the elements above, which in this case is EPC, system integration, and the storage system cost. O&M is set as 0.4% of direct cost. This was based on some studies we did where it ranged from 0.4 to 2%. So we settled on this. Now for longer durations, calendar life can dominate. So the actual duration where the domination goes from cycle life to calendar life depends on each technology and its cycle life. 80% depth of discharge was used as a basis for all technologies, except for lead acid batteries, because most of them, the rated ampere hours is based on the 50 to 100 hour rate. At less than or equal to 6 hour rate, they cannot give you 80% depth of discharge. Next slide, please. General methodology for pump storage and compressed air. Pump storage consists of reservoirs, compressed air consists of cavern. Power equipment for pump storage consists of building a powerhouse underground or underneath the hill, and electromechanical equipment. For compressed air, it is power equipment and controls and communications. But unlike pump storage, there is no underground powerhouse needed. As I discussed earlier, contingency fee is simply 33% of all the direct costs for pump storage. For compressed air, next slide, please. The EPC project development and grid integration costs are included in the above costs. Pump storage cost methodology. What is the type of electromechanical? We have fixed speed, variable speed, ternary. There's not much of variable speed planned for the US, but that may change. Costing done for fixed speed, and add a 10% for variable speed electromechanicals. The reservoir cost obviously depends on the site geography. And it depends on based on the site, you can have upper and lower reservoirs in a pre-existing brownfield mine. or in half of the US projects are open loop using existing lower reservoir. Now, theoretically, higher the head, lower the cost, but we found that there is quite a weak correlation, so we did not explore this. Next slide, please. Round trip efficiency is 80%, and the calendar life is 60 years for pump storage. The breakdown for cost we obtained based on interview with various vendors. We got price for 2 durations, 9-hour duration and 18-hour duration. The cost was given in dollars per kW. And then we were also given the ratio of the civil and infrastructure cost to the electromechanicals cost. So, and based on this, what we did was we were able to back out the electromechanical cost from simple algebra based by taking the difference between the 9-hour and 18-hour. And then we were able to, and based on the relationship that the C&I cost ratio to electromechanicals was about 3 to 4. So we were able to back out the construction and infrastructure cost for the powerhouse. And the reservoir cost, construction and infrastructure for the reservoir was also, we were able to back out. And then we applied standard scaling for as a function of megawatt and as a function of megawatt hours for every, and then the megawatts spanned 2 orders of magnitude. So if it is 100 megawatts, 1,000, 10,000 megawatts. As I discussed earlier, next slide, please. 33% contingency fee was slapped onto the direct cost. For the O&M operation and maintenance cost, this is a detailed slide, and we use this as a template for compressed air also. So I will go through this very quickly. We assign a certain labor for 1,000 megawatts as follows: 32 persons, 100K per person per year. Total labor is known. Parts and consumables. So consumables are about 40% of the labor cost. Assume for each 10 times lower megawatt capacity, labor cost reduces by a factor of 2, not by a factor of 10. That's the scaling effect. Every 5 years, we have to do some minor repairs. Every 10 years, do deeper repairs. Every 20 years, do major overhauls. And we have some cost for all of those. And based on this approach that was provided by the industry stakeholders, the O&M costs aligned with very well with this reference 4. And across this 10 to 1,000 megawatt range, the O&M cost also aligned well with reference 5. We made some slight change in 2022 report by slapping on an O&M cost to the storage portion, also the reservoir portion for greater than 10-hour duration. Next slide, please. Compressed air cost methodology, only 2 plants are operational. The literature review for Power Island and cost is around 1,150 per kW. And this also includes conversation with vendors. In terms of dollars per kW scaling, we had half the scaling compared to pump storage. I didn't mention that for pump storage, it was 16% drop per 1 order of magnitude increase in power. For compressed air, it is 8%. Why? Because there is no underground powerhouse construction for compressed air. Salt caverns have the cost of around $7 per kWh based on conversation with vendors. Again, we apply a slap on a scaling for the cavern costs. Indirect costs are included in the above. Unlike pump storage, where we have to slap on a 33% contingency fee, indirect costs are included in these costs. No cost decrease was assumed for 2030 for both pump storage and compressed air, because the material cost increase is expected to cancel out improvements in performance. O&M costs, again, just like pump storage, was split into labor-related costs and some fixed maintenance costs. And just as in pump storage, the storage energy-related O&M cost was added for durations greater than 10 hours. Next slide, please. The round-trip efficiency for compressed air is 50 to 70% with a calendar life of 60 years. Hydrogen energy storage system, we got a lot of, all the input was from either work by NREL or the Fuel Cell Technology Office. All the cost was taken from reference 1. DC storage block consists of the fuel cell stack, electrolyzer stack, and the cavern to store hydrogen. The DC balancer system consists of water handling units, compressors, gas handling units, blowers, humidifiers, thermal management. Power equipment in this case is rectifier for charging and unidirectional inverter for discharge. Controls and communications, we are using the methodology developed by the BESS, battery energy storage system approach. Markup for system integration EPC project development have been included in the prices that are in reference 1. Grid integration, we use the same approach as BESS. A 2030 cost for electrolyzer, fuel cell system, rectifier, and inverter have been revised from our 2020 report and decreased downward based on input from Fuel Cell Technology Office. And they base their decrease based on the fact that there is a lot of development in heavy duty vehicles for fuel cell systems that will accelerate grid scales, grid storage, and also unitized reversible fuel cell systems. Next slide, please, can also reduce costs. The breakdown for hydrogen energy storage system, we evaluated for 100,000 megawatts, 10, 24, and 100 hours. Assume salt cavern for storage. We piggybacked on our findings from compressed air, but we also included some one data point based on Argonne National Laboratories work that determined the dollars per kilogram of hydrogen, and then NREL work that determined how much kilowatt hours is obtained in discharge from 1 kilogram of hydrogen. And Fuel Cell Technology Office has also provided us some losses related to compressors. So based on this particular data point, that was about $2 per kilowatt hour, whereas compressed air, as you recall, was $6.8 per kilowatt hour. But we added this as one more point and computed an average. The fixed O&M was also reported in reference to, but we excluded these items: property tax, insurance, permitting, and licensing. For stack replacement cost, what we did is the stack replacement for electrolyzer and fuel cell is based on cumulative energy throughput. And to estimate the cumulative energy throughput, we need to know what the discharge and charge capacity factors are. Obviously, the round trip efficiency for hydrogen energy storage system is about 0.33, which means the charge duration has to be much greater than the discharge duration. Based on this, we were able to calculate the cumulative energy throughput over the life of the system, and when it reaches its upper limit, we have to replace it or replace the stacks. The cavern storage system, just like in compressed air, the O&M is 2.1% of capital cost. Next slide, please. We assume the O&M cost to remain the same for 2030. Gravity energy storage is different. In the top right, you see gravity where the bricks are lowered and raised. When you lower, you discharge. When you raise, you charge. In the bottom left, you have got a piston that moves up and down. Water is pumped below the piston during charge, and then the piston comes down during discharge. On the bottom right, you got a rail car, multiple rail tracks in a hill. That when you rail cars are moved up, that is charge, and when they come down, that is discharge. That's what this slide says. Essentially, I will just look at this heavy bricks. The power scales with the number of arms in a crane and the size and number of motor generators. Energy scales with weight and number of blocks. Power equipment's cost is similar to pump storage, hydro. I'm going to skip the rest. Next slide, please. So for the pressurized water system that I mentioned with the piston going up and down, the scaling is significant in terms of both energy and power. When you increase the diameter, for example, you can actually increase the energy by raised to 4 because it scales in terms of D raised to 4, diameter raised to 4, and height raised to 4. And if you set the diameter is equal to height, you get a lot of scaling effect. For EPC fee, project development and grid integration costs, we do 20% of markup to the sum of to all the direct costs, which is less than the 33% contingency fee for pump storage, which is understandable because we don't need a FERC hydro permit. For at 100 megawatts, gravity systems seem attractive at greater than 24 hours, whereas at 1,000 megawatts, they seem attractive at greater than 8 hours. O&M costs set same as pump storage for piston-based systems. For the other systems, we got input from the vendors or developers. Calendar life is 49 years. Round trip efficiency is 83%. Next slide, please. Response time has a wide range of 1 to 17 seconds. The rail cars being a slower response. Thermal energy storage is quite complicated. There are several types of systems. We are doing electricity in and electricity out. Some we have hybrid systems such as fuel input. We have pumped heat energy storage. There are no demos. It is low technical readiness, technology readiness level. Sensible heat, you can heat molten salt, sand, concrete, thermal oil, liquid energy storage. O&M cost varies with technology. Sand-based systems have the lowest cost. Liquid energy systems have the highest cost. Next slide, please. Round trip efficiency is in the 40 to 50% range, and the calendar life is 35 years. This is sensible heat energy storage. On the right, you have got a graphic of the cost breakdown that we got from reference 1. This formed a foundation for how we costed out a sensible heat storage system that have got a steam power plant, for example. There are different types of sensible heat: active heat, passive heat. Active has got direct, when the storage medium serves as the heat transfer fluid. Indirect is when the heat transfer fluid exchanges heat with the storage medium. Active is when the storage medium actually flows between the tanks. Passive is when the heat transfer fluid flows through the storage medium, such as, say, a concrete. And you have hot air flowing through pipes in the concrete, for example. Molten, if you are talking about molten salt storage, the tank diameter maximum is 13 meters and height is 13 meters, diameter is 40 meters. It can store 30,000 tons of molten salt storage capacity. Individual costs, as I mentioned, are obtained from this reference 1. The cost split is given in that graphic there. EPC fee is 10%, project development is 20%. Next slide, please. And some systems have fuel input, as I mentioned earlier, that will use a combined cycle plant. This is a pumped heat storage system, operates on the closed Brayton cycle. That means you got either air or a supercritical carbon dioxide, and then it will use an air gas turbine. It has a low TRL level. Depending on the fluid inlet and temperature and pressure, you need, these are different for the discharge turbine and the charge compressor. So that is why typically they use separate turbines and the compressor, turbines for discharge and compressor for charge. There's a single motor generator can be used, but in order to save cost. But if the charge rate is much less than discharge rate, the motor operates at partial load. That is inefficient. Procurement is typically is done such that when you procure a compressor, it comes with a motor, and when you procure a turbine, it comes with a generator. So it makes no sense to use a single motor generator. Electricity is used to transfer heat from cold storage to hot storage during charge. You pump the heat up, and then you drive the heat down during discharge. And that heat during discharge heats up air or supercritical carbon dioxide to run a gas turbine. For long durations, we can use ammonia as an additional heat generation system. You burn that with air. Ammonia is generated in an electrolysis system, and then you can supply extra heat to run long duration systems. The RTE, as you know, for theoretical RTE doesn't depend on the maximum temperature, which means you can use sand storage system with a lower upper limit to reduce cost for the use low cost carbon steel for sand silos and conveyance. Next slide, please. And if we have time, I can go through these figures at the end if anybody has questions, but I'm going to leave that for the end. A liquid air energy storage system. Essentially, it has a refrigeration system for charge, storage vessels for storage, and obviously a turbine generator for discharge. During charge, a refrigeration cycle cools the air and condenses it to cryogenic temperature. Heat generation generated during compression is stored in the storage medium. On the right, you can see upper right, you see a heat storage in red. That's where the heat is stored. Cooling in the refrigerator cycle supplemented with cold, supplied by cold storage medium. You see just below the hot storage, you see the cold storage medium tank. Okay, so the cold storage occurs in the discharge cycle when liquid air is pumped to high pressure and warmed in a heat exchanger. Unfortunately, I don't have control, but you can see the cryogenic feed pump. Liquid air is being pumped, and then that cools the cold storage medium. And that cold is what is used to supplement with cold in the cooling in the refrigeration cycle. And the warm liquid air is further heated in the heat exchange with heat from the hot storage medium, and it runs the generator. Alternate approach in the bottom is instead of using hot storage, you use fuel to generate heat in a combustion turbine and provide heat for liquid air and for low temperature organic Rankine cycle. Courtney had flagged this correctly. It should be capital R here for Rankine. Okay, so the advantage is that you can use fuel and it increases the efficiency in one way, but in another way, since you're not using hot storage, you're not capturing the compression, heat from compression during charge cycle. The tanks used are massive, 20,000 cubic meters of cryogenic tank, standard size for liquid natural gas storage. It can store 75 gigawatt hours of discharge energy. So that is why this makes liquid air as an attractive, potentially attractive option for long duration, especially if you've got hot storage along with supplemented with fuel such as natural gas. I think I am done. Next slide. Yeah, over to Kendall. Thank you.
Thanks, Vish. Let me see if I can get my video going again. All right. So Vish just went through a deep dive into our methodology, and for the rest of the presentation, I'm going to walk through basically some of our results at a high level, starting with the total installed cost comparison. Then I'll talk about the levelized cost of storage and go through some of our results there. But it's going to maintain a pretty high level overview. Due to time, I'm just going to go through some key takeaways because just based on this figure, you can see that there's a lot of detail, and based on what Vish was talking about, there's a significant amount of detail that we've done as part of this project. So if you're interested in digging into this a bit more, including some of the results that I'm walking through, I encourage you to go check out the report or go and look at the figures on the website, because we're going to keep it pretty high level here for time. So this figure that you're seeing right here, just to orient you, this is showing the total installed cost estimates for 2021 in dollars per kilowatt hour for every single technology. You can see each row is giving the power capacity and storage duration combination that we have the estimates for, and each technology is represented by a different color and shape here. So as I mentioned, I'm just going to walk through some high-level takeaways. I'm also going to have it point to them just so you don't have to squint at your screen to see what I'm talking about. But right off the bat, a big takeaway is that compressed air energy storage is giving us the lowest installed cost estimate for durations greater than or equal to 4 hours. It's about $122 per kilowatt hour for a 100 megawatt 10-hour system. You can see it in this diagram. It's represented by this blue circle here, where for 10 hours, it's pretty substantially beyond the other technologies. And at 4 hours, it is still pretty beyond as well. Moving on, we can see that looking at just the battery storage technologies, they tend to fall roughly in this range of about $300 to $600 per kilowatt hour for 2021. There are some that don't fit in that range. For example, this green X here is showing redox flow, where at the lower energy durations, it's really not nearly as competitive with the other battery systems. And to be able to become competitive, you would need to see a pretty significant electrolyte drop there. Lithium ion, which is represented by this orange square, pretty much leads the charge for every single power capacity and energy duration combination for total installed costs. The only places where you see it start to fall a little bit behind in order is at these really high duration, where you see vanadium redox, these green X's really start to take the charge as you get into higher and higher durations there. Moving on to 2030. And looking at the battery storage systems again, we see this shift down. So previously I mentioned that they tend to fall in that $300 to $600 per kilowatt hour range. Now we see it in that roughly $230 to $500. And this is of course not including those larger estimates at the lower durations for vanadium redox flow. And you've also got some zinc and some lead acid that are at the higher end of the range at the lower durations. Lithium ion LFP systems, they are still leading the charge, even more so in 2030, to the point where redox flow doesn't actually surpass it in 2030. You can see that green X is in second place there. But what's interesting to see is that the 100 megawatt 10-hour duration, we see lithium ion LFP starting to become equivalent to or surpassing the installed costs for pump storage and thermal systems by 2030. And then lastly, just last thing I'll point out is that compressed air, it still maintains a really low cost status that we saw in 2021 at durations greater than or equal to 10 hours. However, we see that the hydrogen systems really start to match or even surpass them at these durations as well. So you can see that shift down there where hydrogen is really starting to take the lead. So for the rest of the presentation, I'll talk about the levelized cost of storage. It's not going to be in a huge amount of detail here just for time. If you want more information on what I'm talking about, I encourage you to look at the report. There's a pretty large section on this in there. But for those of you that might not be familiar with what the levelized cost of storage measures, it's essentially getting to what is the average revenue per kilowatt hour discharge from the system that we need to make so that we can recuperate all of the costs that we spend on installing and operating a storage system over an analysis period. So we're now including costs that go beyond that total install cost. We're also including operations and maintenance, large capital expenditures for replacements, augmentations, major overhauls, electricity charging costs with round trip efficiency losses. So all of those costs really need to be considered. And this gets us to a metric that we can use to sort of compare these different storage systems on an apples to apples basis and actually start looking at them over their operational lifetime rather than just an installed cost. So the 2022 report does include some new enhancements for this metric, including one thing I've already mentioned, which is augmentations, replacements, and major overhauls, where for this report now, we've set a minimum life of 20 years for battery energy storage. So it's going to be between 20 and 25 years for their project life. However, your cycle life or your calendar life are going to place limitations where you're going to have to replace that storage block or augment that storage block to maintain your operation for that time period. So we've now incorporated all of these different replacement schedules or augmentation schedules into this LCOS calculation. In addition, we've fine-tuned how we determine the output of the storage asset. So now including a bunch of items such as duration, round trip efficiency, at the specified depth of discharge, what it's operating. We also include warranty cycle limitations. So for example, if your battery system warranty limits how many cycles per year that you can operate to still maintain that warranty, we've involved that there. And then we also include things like rest time between charge and discharge, which varies by technology as well as the power capacity and energy duration combinations in some instances. And we've also included construction periods for each technology, so shorter for battery systems than for the larger systems. And then there's also some sensitivity analyses that we conduct around the inclusion of recycling costs at the end of life. And then we also look at an extended analysis period. So just as with the total installed costs, I'm going to do a pretty high level overview, just observing some of the trends we see. I'm just going to keep it to the 100 megawatt, 1000 megawatt situation here, just because that's where we can see most of the technologies and we can start pointing out some of the differences. And I can show you this nice graphic here. If you want to see the 2030 or the other power capacity comparisons, I encourage you to go check out the website. So just to orient you as well, the LCOS is being measured top down here. So you can see higher is obviously higher. And then going from left to right, you have the energy duration or storage durations, and these are categorized by the 100 megawatt and 1000 megawatt systems here. And then of course, each technology is split out into its relative color and shape. So right off the bat, with kind of the same we see with the total installed cost, compressed air has the lowest LCOS of the technologies for these combinations of power capacity and duration. And this is due to its lower unit energy capital cost. So really leading the charge there with that. However, the others are really not that far ahead or far beyond, I should say. Another pattern that we notice, and this is consistent across the other power capacity and plots as well, is that you start to see at the 2-hour range, you've really got your battery systems they're more spread out than you see at the higher duration. So I've drawn this triangle here showing how the gap between the battery system, it narrows pretty consistently as you get towards 10 hours. So in the 2-hour range, you're seeing roughly between 20 cents and 30 cents. And then by 10 hours, they all tend to aggregate around that 19 cents per kilowatt hour range. The only one that does not come down as much is lead acid, and that's because we see a lot of constraints there with its cycle life, where we're having to replace that storage block more often to meet that project life, and that adds up in terms of cost. And then lastly, I drew these lines over here just to kind of demonstrate what I'm going to talk about just through a few of the points. We see this trend where most of the battery systems will find their lowest point at the 10-hour range, and then past that, for battery energy storage systems, we see this pretty substantial hike going from 24 to 100-hour systems. So for example, as you can see right there at the 10-hour range, most of the battery systems are about 20 cents a kilowatt hour. And then we see this huge diversion and these huge gaps opening up by the 100-hour range. We've got a lead acid system all the way up to $1.30 per kilowatt hour. You can also observe this trend in the non-battery systems. I drew the line for pump storage over on the right-hand side there. And it's showing that it still does increase going from 10 to 24 to 100-hour systems, but not nearly as substantially as you see for the battery energy storage systems. And you can also see it a little bit for compressed air there as well, but again, not nearly as substantial, showing that these really maintain their low cost status at the longer duration systems. So we've thrown a lot of information at you. There's a lot of detail here and a lot that we didn't even touch on. So if you are interested in finding out more, the other part of this entire project is to build this website and database so that this information is all accessible. We have both reports up there, the 2020 report and the 22 report are both downloadable. I encourage you to check those out at that link. And then there's also a bunch of interactive visualizations. You can see an example of one of the tables here for lithium ion, where you can go in and you can select the power capacity and energy duration that you're interested in. The table will automatically update with the estimates. You can see low, point, and high estimates in the 2021 and 2030. And there's also interactive graphics for LCOS and the installed cost comparisons that we showed you. But there's a lot of information. It's pretty cool. I encourage you to check it out. And I think that's where I'm going to wrap it up. And I think we've got plenty of time for questions. So I will stop there. Thanks.
Thank you, Kendall. Thank you, Vish, very much for the presentation. We've got a lot of questions that have come in. So let's start off here. I think, let me pull this back up real quick. When we look at, one of the questions that's come in is how do we handle overbuild and, augmentation into this calculation? So, if they overbuild the initial system, how is that captured in our either cost estimates or in the levelized cost?
Vish, do you want to start that one off, and I can add in some details for LCOS?
You're on mute, Vish.
Yeah. Okay.
There you go.
Yes. What was the question again? I lost my train of thought.
Oh, just how do we handle the overbuild?
Prior to that, you had another question.
Capacity, at the start. How do you do that? And then another one was, how do you handle the augmentation?
Yeah, I wanted to address the augmentation part. Thank you. Suppose you have a battery. I'll keep it very simple example. Its cycle life is 2000 cycles and you do 400 cycles per year. Then at the end of 5 years, you have to replace the battery, but it's not as simple because we are doing an 80% depth of discharge. And say a lithium-ion battery, as Jim McDowell advisor, he's here in the audience, suppose their end of life is 60%. Then it has got at 80% depth of discharge, at 80% of remaining energy, it still has half the energy life left. So then what we do is we add more storage system and then run the entire storage system at 60% depth of discharge and augment it. In some other case, in a fuel cell and electrolyzer, the cumulative energy throughput is the limit. Once it reaches that cumulative throughput, we just replace it. Over to Kendall.
Yeah, just to add on to that, we incorporate into the LCOS calculation by essentially determining at what point, based on the depth of discharge that we're using, would that storage block need to be replaced or augmented, and then that capital cost either as a full cost of the storage block replacement or some other determined cost that's incurred in year X, and we're bringing that into the calculation as a capital expenditure.
Okay. So another couple questions that came in talked about how we handle the price volatility. As we're aware that, as we got into the supply chain issues, we saw, we would have a cost estimate and that would change on a monthly basis here almost. I guess I can try to take part of that if you want. And then another question was, do we factor in anything in terms of material supply issues into our cost estimates? And so I guess I'll let you weigh in. I'll give you my take on it. And, that is a difficult problem that we saw, was this volatility in price information. And I think the important thing that this project was setting out to do is, one, provide a systematic approach towards looking at these storage systems and making people aware of everything that goes into a storage system. We tend to see the price of a lithium ion cell and not realize here's the power electronics, here's the grid integration on that. And so those are still valid. We're trying to give a range, and a kind of an expected estimate of that cost. But yeah, we are not able to capture, those short-term price changes within what we're doing. And so that will have to be taken into account, but you have a systematic approach that if it does change, you should be able to go in and still use that baseline to calculate, an estimated cost for those systems. In terms of supply chain, it's not really something we've looked at. We've looked at going deeper into this system, but yeah, we are just using kind of the what's available on the street and not factoring in that availability. And so Kendall, Vish, I don't know if you've had anything to add to that.
I would like to add something on Jim McDowell's question on are you assuming unlimited, that I don't remember the question, and if you could read that, or unless I think his was, are you assuming that there is going to be plenty of lithium available, whether it's lithium, nickel, cobalt? We are right now, we haven't taken that availability into account, as Vince mentioned. I would like to add that our one of the reasons is that recycling right now is in its infancy. But as the recycling gains foothold, and there is also the second use of battery that's already there, it has gained ground. So in 10 years, all of those batteries will be coming offline and the recycling would be getting its act together. And right now, the carbon footprint for recycling is quite high. So once those issues get resolved, our hypothesis is that that would take care of the materials on a limitation. Thank you.
All right, thank you. Hey, Kendall, we had a question on, in addition to the levelized costs and the installed costs, would it be possible to calculate a capacity payment metric for the different technologies? That's $1 per kilowatt year metric, because many of the energy storage deployments will be valued as capacity assets. Do you have any insights into that?
I don't see why we couldn't. I know in the past there's a wide range of cost estimates that get provided across different research, and one of them gets to an annualized payment, so getting to the point right before you're doing it on $1 per kilowatt hour output. So essentially, the way I would approach that would probably be to take that annualized payment of all-inclusive costs and take it by the rated capacity. So you're getting to a capacity-based annualized payment in that case. So I think that would start to at least get at what that question is asking. But yeah, I don't see why not, why you couldn't just keep expanding the different types of metrics that you're providing.
Okay.
If I understood that question correctly, you get paid if there is an application that pays you for power, then you get paid for that. Our levelized cost is, to the best of my knowledge, is not taking into account any revenue streams for energy related. So in the similar vein, we are not going to be taking into account any revenue streams from power. Maybe I have misunderstood the question.
I interpreted the question maybe slightly differently. I think it's more of just rather than like, in addition to the LCOS, which is based on the revenue per kilowatt hour output, they're asking about finding some all-inclusive cost that's based on the rated power capacity as well.
So we had a couple questions about the report. I know Kendall had it there on her slide at the end. I did put a link directly to the downloadable report into the chat. So hopefully you have a chance to see those now and be able to get access to those. So another question that came in, one, is there any cost information for storing hydrogen, gaseous hydrogen in cylinders at 5,000 to 10,000 PSI?
There may be out there, but we didn't look for it because our hypothesis was that it was way too expensive to to take that into account. So we address compressed air using storage options that would make the most sense right now.
And I think another point too on like hydrogen, we were only evaluating the bidirectional capability. So electrons in and electrons out. I think we all realize there are multiple different pathways on hydrogen and do that. And there may be different storage options in there, but really had to narrow it to kind of select what we think the most equal comparison point is for that hydrogen technology. So another question, you know, we have this systematic kind of breakdown of it from the storage block, the balance of system, you know, and then you get into the grid systems integration, EPC project development. You know, a lot of questions around what's the overlap between those and how do you break that apart? I don't know, Vish, if you want to try to handle that, what the demarcation is between those different areas.
Yes, it's a very complex topic because you can have a one developer who would be an EPC, but that will also do system integration. Another organization may do project development, but they will also own the whole project. They will do the EPC, engineering, procurement, and construction, and system integration. There are some battery developers or manufacturers who do the system integration. So that is why the demarcation sometimes is not very clear. Having said that, the markup for each category, such as system integration, EPC, and project development that we have provided, that we expect to be in place regardless of whether one entity is doing all three or whether one is doing two and another entity is doing the other.
Okay. Kendall, I guess I'll direct one to you. You know, as with DOE, they've set a very aggressive target for reducing the levelized cost of storage of these technologies. For a technology developer, you know, there's all the variables that go into calculating levelized costs. You know, what do you see as their primary developments that they can do to improve that overall levelized cost of storage?
That's a great question. I think it's going to differ by technology type based on what's driving that cost. So obviously for some of them, like for lead acid, you see its LCOS is so high because its cycle life is restricting how long you can operate it before you're going to need to replace that storage block. Whereas others like lithium ion is going to be primarily driven by that storage block cost component and things like that. So I think it's really going to vary based on the different characteristics of each technology.
So basically, we can still use that as the method to go through. Here's what the improvements in round trip efficiency are going to gain you, and here's the lifetime of the systems.
I think it would be interesting to kind of do that analysis and deeper dive and kind of adjust all those levers for each technology, so to speak, to see what are the returns on LCOS, dropping LCOS when you improve round trip efficiency by this amount. What happens if you improve the storage block cost, and how does that relate to the other components that are based off that cost? So if fixed O&M is if we're calculating as a certain percent of other components, there's obviously going to be some connections in there. So I think there's a lot of room for really interesting analysis there that can get into that detail that's going to vary by different technology types.
Okay. Thank you. We had a point of clarification. So when we looked at compressed air, we were looking at systems that required burning of natural gas to get the electricity back out. Is that correct?
Yes.
Systems. All right. So some of the other ones, oh, go ahead.
No, sorry.
Oh, sorry. The question on there, you know, looking at how does the footprint of the system come into play into our estimations? You know, if we're a lower energy density system that has, needs a much larger real estate, where does that come into play as we look at the cost breakdown?
Yeah, we have to be very candid. In this go around, we did not take the footprint into account with the assumption that that may not be the most critical for stationary storage compared to transportation. Having said that, I am hearing some diverse opinions on that topic. So that would be something for us to consider, and we welcome folks over here to provide their input based on their experience as to what would be the right approach.
Okay. And this you had mentioned earlier, I think in your discussion about ammonia in place of hydrogen. Any idea of how that compares for long duration storage applications?
That ammonia was in the context of pumped heat storage, and it essentially you use electrolyzers. So a very good question, Vince, because you are using an electrolyzer for that as well, and they provided an electrolyzer cost. Unfortunately, I don't have it the top of my head right now, but it seemed like the electrolyzer cost in dollars per kW seemed to align with the electrolyzer cost that we are using for the hydrogen energy storage system.
Okay.
There is one question in chat that I would like to address. I think Will mentioned C rate definitely matters as it affects the cost of purchased energy during charging, allowing reduction of discharge costs. That in turn allows higher capacity factors, which reduces the capital amortization. Very good point. Now, the thing is, when we talk about a 2-hour rate, then what is the 2-hour rate? The DC battery can have a 10C rate, for example, but the 2-hour rate is determined by the power conversion system. So if we want to capture that additional higher charge rate capability, we will have to get a power conversion system with a greater rated power. When we do that, so suppose it's a 1 megawatt is the discharge. And so if we get a 2 megawatt power conversion system, then during discharge, it is operating at 50% of its rated power. I know at 50% of rated power, these systems have a reasonably good efficiency. It's A, you're overpaying for that power conversion system. B, you may adversely affect the efficiency of the power conversion system as well. So if the question's intent is due to that, we should reduce that duration to 1 hour, then point well taken. We can charge over 1 hour and discharge over 1 hour. But for the 2-hour duration, it seems like the power conversion system will be the one that will limit the charge rate, especially for batteries that can handle C/2 rate charge. Thank you.
All right, thank you. I know we're coming up against the top of the hour here. I want to thank you all for the questions, and thank you, Kendall and Vish, for the presentation. I did want to highlight some of the upcoming presentations that we still have in this series as we go through. So October 20th, Jason Zong will be talking about silicon-based lithium-ion batteries. And then on November 3rd, Chin Wong will be talking about insights into lithium-ion battery degradation by the calorimetric approach. And then we will look at, on November 17th, high throughput capabilities that we hear for testing and developing new materials with Yang Yang and Witness Martin. So I want to thank you all for your time again, and thank our speakers. If you do have questions, you can either reply to Laura directly. I think who helped was on the registration, or you can go to the PNNL website and find our emails, Vish, and it's on the report also for myself. So please feel free to reach out to us if you have any additional questions, and we'll try to get those answered. But thank you all again for your time today, and look forward to seeing you on October 20th and any other future seminars we may have. Take care. Thank you.